Okay, we are at section 19.5, magnetic force on a current carrying conductor. So let's share the PowerPoint, and this is the, I guess this isn't, is this in yeah, it is in the book. It's figure 1913. So we have a little setup here. Battery powers a little circuit with I don't know, just a little maybe it's a nail or something like that. I can't make it out from the detail, but you can see that there's a magnet, and it looks like the north is on the top and the south is on the bottom. So the magnetic field is going downward. And when you flip the switch, what happens? Well, our good old friend Walter Fent is going to help us um, in this case. Oh, I should have turned it off. The same setup, the plus on this side, the minus on this side. You got a magnetic field with the north going down. So let's turn on well, turn on the switch. You're going to see that in this case, the magnetic field is downward. The current, the conventional current, positive, is going to be going into the drawing, so the force should be towards the center of the magnet. Let's turn it on, and sure enough, current flows. You can see the red, the magnetic field, the red flow of current. So the force is towards the magnet. We can reverse the current, and you can see that it's out now. It's down, out, and the vector is that way. So there we can kind of visualize it with the help of our friend Walter Fent. And let's go back to the PowerPoint. So when we have a current in a conductor in a magnetic field, there's a force. So when there's no current in the wire remains vertical. When the current is upward, the wire deflects to the left. Now look at all those green X's. That green X's mean that the uh, magnetic field is going into the page. Now, if the magnetic field is going into the page and the current is going up, that's a charge, a positive charge. A conventional current is a positive charge going up, and the force is that way, is in this direction. When the current is downward, the wire deflects to the right. So we put the magnetic field, the velocity or the current direction, and the force is that way. So it's exactly what we would expect. Now here we have a magnified view. You can see the green X's. The magnetic field is into the page. So magnetic field into the page. There's the thumb is a velocity, so the force is going upward. Now let's so force is equal to Q times the drift velocity times B for that single particle. That Q has a drift velocity of VD, so the force on it is equal to Q times the drift velocity times the magnetic field. Now let's look at, there's a volume from if we take the cross-sectional area of the wire and times the length, that's a volume, A times L. And the number of carriers, the charge density times the number of carriers per unit volume times that volume will give you the total charge carriers. So the force, the maximum force is QV times the drift velocity times B times NAL, and which just the QV, the Q times drift velocity times NA is the current. So you see the current is NQV drift times the area. So the force is equal to B times the current times the length. Now, that formula, BIL, only holds if it's the magnetic field is perpendicular to the wire. If there's an angle, then it has to be force is equal to BIL times sine theta. So you have to be careful when using that. The BIL only applies when the current is perpendicular to the B field. Now, this is some applications. If you look at a speaker, you notice how the north is in the center and there's two south poles around the outside. Well, let's do the right-hand rule. The magnetic field is up. The current, notice the dot, so the current is on the upper side is coming out of the page, so there's a force inward. You can see the F, the blue arrow, the force is inward. Now let's do it for the bottom. We've got the magnetic field going down, and now the velocity, you'll see the red X's, that's the current, so it's going into the page, and again the force is into the base of the magnet. So as you get an audio signal into this that goes back and forth, this cone is going to go back and forth in time with the sinusoidal signal fed it. So if it's 1,000 hertz audio tone, guess what? The paper cone is going to vibrate at 1,000 hertz, and you'll hear a 1,000 hertz signal. So that's the way a speaker works. Here's another. This is an electric, what do they call it? The electromagnetic pump. So things like when you're doing, when you need to pump blood magnetically, or let's say for dialysis, if you need to keep the liquid flowing, you have a magnetic field, you're passing a current through the liquid, and that force, that gives you there's the current, so it gives you a force and gives you a velocity in that direction. That velocity is not the velocity of the current. That the I is the current, so the V is the velocity of the liquid, and so you can move some liquid without damaging the any like blood cells or anything like that. So that ends our 19.5 section. The next section is magnetic torque, and we'll be able to understand a little bit about motors given this.